Ladies and gentlemen, welcome to my talk. My name is Peter Marvidel and I'm with Technical University or TU Dortmund in Germany. First of all, I would like to thank the organizers for inviting me to give this talk. I really do appreciate this. The talk is entitled Enhancing Cyber-Physical Systems with Machine Learning, Drilling Holes into the Walls Between Disciplines. This title contains the term cyber-physical system, and therefore I would like to make sure that really everybody in the audience understands this term as precisely as feasible, and therefore I would like to refer to a couple of descriptions of this term. The term is extending the scope of the term that was used earlier on, which is also essential for your conference. It's the term embedded systems. Embedded systems in turn can be defined as information processing systems embedded into a larger product. So we talk about information processing in a car or in a train. Now, with cyber-physical systems, we are extending the scope in that we are also including a view on physical components. Cyber-physical systems can be defined as integrations of computation with physical processes. So in the cyber-physical system, we do have the cyber-physical system, and we do have the cyber system, and we do have the physical system. In order to make sure that you really understand the term as precisely as feasible, I'm also referring to descriptions by certain societies. And I'm starting with the National Science Foundation, or NSF, in the US. The NSF wrote, cyber-physical systems are engineered systems that are built from and depend upon the synergy of computational and physical components. So you see that we have the expected reference there to the cyber world and the physical world. But then they go on and write emerging CPS will be coordinated, distributed, and connected. And that means in addition, they expect that these systems also provide some kind of networking. A little later on, there was a society called Acatec in Germany that also wrote a report on cyber-physical systems. I will be jumping over the details there and mention only that already from the title of that report, we could have a look on some affected areas, including mobility, health, energy, and production. And I will refer to those in my talk a little later on. Another description was provided by the European Commission. The European Commission wrote, cyber-physical systems refer to next-generation embedded ICT or information and communication systems that are interconnected and collaborating, including through the Internet of Things, and providing citizens and businesses with a wide range of innovative applications and services. So again, we have this reference to the expected networking. And then also we have a first reference to the expected services that are to be provided by cyber-physical systems. The European Commission also wrote, often endowed with control, monitoring, and data gathering functions, CPS need to comply with essential requirements like safety, privacy, security, and near zero power consumption, as well as size, usability, and adaptability constraints. So we see there that in addition to networking, we also expect some control system to be included there in the cyber-physical system. And for the first time, we see a reference to data gathering functions. That means we care about the data that is generated by the sensors. This data may have a non-obvious interpretation, which means that we need data analysis, for example, machine learning. Furthermore, we see some properties that are expected there, and I will refer to these properties a little later on in my overview of challenges that we see for the design of cyber-physical systems. So using these descriptions of cyber-physical systems, I hope that you are now able to provide answers to the questions that I put here on this slide showing the outline. The question was, what are cyber-physical systems? And using the initial slides, I think I have provided answers to this question. This outline also shows the other sections of my talk. Next, I will try to answer the question, which opportunities do exist and which challenges do exist. This will be followed by a presentation on how machine learning can improve the usability of cyber-physical systems and how we are using machine learning for getting meaningful results out of our sensor values. This will be followed by a brief section on CPS education, and of course, finally, there will be a conclusion. So which opportunities do exist for cyber-physical systems? Opportunities do exist in many different areas, and I'd like to start with transportation, where for all means of transportation, we see an impact of the availability of cyber-physical systems. So no matter whether we design cars or trains, the availability of these systems will have an impact. The second area is that of smart production, where also the availability of CPS will have a major impact. For example, we can get away from rather strict pipeline-based processing and use, for example, production islands. They allow us to have a more flexible production where we are tailoring products towards the needs of particular customers. And in the extreme case, we can think about a so-called lot size 1. That means we have a special design for a particular customer. Overall, this integration of the cyber world with the physical world leads to the term Industry 4.0, referring to the next generation of an industrial revolution. This is extending the term Kanban that was used earlier on, which refers to some kind of just-in-time production. There are more sectors affected. The health sector is very important, in particular for the people, because we can have advanced diagnosis technologies, including advanced sensors. One of those will be presented later on. We can have more personalized treatment and enabled by advanced sensors. We can have assistive technologies because we can have special help for the handicapped people. And there can be result monitoring. That means we can monitor the impact of medication for particular patients. Smart homes are a fourth sector where we can try to generate as much energy as we consume, so that effectively we have a zero energy home. We would like to provide maximum comfort and security, and especially in aging societies, ambient assisted living is important. Now, as a presenter, I would like to make sure that I meet the expectations of the audience. And I know that, especially abroad, people assume that Germans care a lot about beer drinking, and I would like to demonstrate that I care about beer drinking as well, at least as far as is concerned, as this presentation is concerned. So this is a not so serious slide on beer drinking. We see a large hall, for example, at the Munich Oktoberfest, where there are lots of people, at least before the pandemic, drinking beer. They all have a mug. And with this large set of people, there is a danger of mugs becoming empty. And I would like to propose that we produce a so-called smart beer mug that comes with a capacitive sensor. And whenever there is a risk of this beer mug becoming empty, we can use additional electronics to alert servers so that the servers can look for those people that need a refill, and in this way keep the customers happy. Now let's go back to more serious applications. We all know that the future smart grid will work only with CPS systems. We know that we would like to recover faster from disasters. Public security is an issue. We had some artificial structures that were recently breaking, like dams and bridges. We can try to avoid this with putting sensors there. Scientific experiments use a combination of cyber and physics, and they are therefore special cases of cyber physical systems as well. And robotics, defense systems, and telecommunications are really at the root of cyber physical systems. They were the first cyber physical systems that were used. Now, I did not make this list this long because I intentionally wanted to bore you with a long list, but because I wanted to convince you that almost every industrial sector will be affected by the availability of CPS, and that those of you who know how to design a cyber physical system have very good chances of finding a job. However, such a job would come with some difficulties because it may be challenging to design a cyber physical system. And the challenges include, and this is my number one challenge, dependability. Dependability has a couple of flavors, and I would like to start with safety. These systems should not cause any harm to users or not to animals. They should be reliable, that means they should not break, in contrast to this little aluminum wire over here, which seems to be melting away. We are connecting our cyber world to the real physical world, including physical time, and that means our computations have to finish within the available time. Also, sometimes we are operating our devices outside the specs. Still, they should not behave completely unexpectedly, and therefore we need so-called resilience. These systems should be secure. That means outside hackers should not be able to cause any malfunction of our system. And obviously, private information should remain private. Now, there are more challenges as can be seen from this long list. There is energy efficiency because these systems are in many cases portable systems, so we have to carry around the energy, or we have to use energy harvesting. In both cases, only small amounts of energy are available. We are going towards higher performances, which also increases the likelihood of having thermal problems, and we have to add thermal management there. We have a mismatch between the cyber world and the physical world. For example, there are real numbers in the physical world, and there are no such numbers in the cyber world. We use our systems in a very dynamic environment. We are using them in a changing environment, and they come from various sources meeting various standards, so they are in a way very heterogeneous. We do have issues with the human interface, which currently is not as nice as it should be. In many cases, at least, there are social issues. We should not have completely unexpected social results. There are legal issues, and from embedded systems, we inherit the fact that we have to care about many objectives like the sizes, the cost, and the disposability. The last line corresponds to the information that is coming from the sensors, or more precisely the values that are coming from the sensors. Their interpretation may not be immediately obvious, and we need data analysis techniques like, for example, machine learning. So there are lots of challenges, and I would like to mention one additional challenge that is really key for this presentation. And this is shown in a little less serious way. We look at the fact that knowledge from many different disciplines need to be available in order to design a cyber-physical system. And this includes knowledge from computer science, from electrical engineering, from physics, from various areas of artificial intelligence, mechanical engineering, mathematics, life sciences, etc. So ideally, we would be tearing down the walls between the different disciplines. However, if you look at this animation, you will see that there is no realistic hope of this happening. So we have to be happy if we are able to at least drill holes into the walls between disciplines. The fact that linking the different disciplines is difficult is something that I would like to demonstrate with using a small physical example. So in this movie, you're going to see a real physical example. It is the famous example of the bouncing ball. So you see that there's a ball which is bouncing and which is jumping up in a way. Now I would like to model this simple physical experiment in a language of computer science using, for example, Modelica. In Modelica, we do have in this model a couple of declarations. These are less important for this talk. I'd like to look at what's considered to be key in the context of this talk. I'd like to look at the partial differential equations. We see that the velocity is the derivative of the height, and the derivative of the velocity is the acceleration, which is resulting from gravity. In the simulation model, we can further create a kind of event that's generated when the height becomes 0 or even less. Then we reinitialize the velocity. Results can be seen on the right side of the slide. You see that in red we show the trajectory of the ball, and in blue we see the velocity. So we see when the ball reaches the surface, we then are reinitializing the velocity. It suddenly becomes positive, but you see that the initial velocity after each iteration becomes a little less because there is some kind of attenuation there called S, and S is in this particular case 0.8. However, I haven't really shown you the full result generated for this model because the simulator would show a result as shown on this slide, where you see that after some time the ball seems to be tunneling through the bottom and the velocity is increasing again. This is resulting from the fact that we cannot really look at the situations that we have for extremely small numbers. So when the height becomes close to 0, this event is no longer generated and reflection does not take place, and we have to repair the model. We can repair the model by assuming that the ball gets stuck to the surface once the velocity becomes less than a certain threshold, and if this happens, the velocity is then reinitialized to 0. And over here you see now the full simulation result. So this demonstrates that you can easily run into problems if you would like to link different disciplines. Now next, I'd like to show you how the design of cyber-physical systems can really benefit from providing data analysis using, for example, machine learning, and using this as a special case of drilling holes. I'd like to present 4 different research results that are based on results from our so-called Collaborative Research Center 876, which is supported by the Deutsche Forschungsgemeinschaft, or DFG. The first one is the so-called Pomono sensor. The Pomono sensor is an advanced sensor for biovirus detection. Bioviruses are potentially smaller than the wavelengths of light, but of visible light, but still you can see them in visible light because of a so-called plasmon effect, which is in a way enlarging the impact of these viruses in the visible domain. The key function of such a sensor can be seen in this schematic diagram, where we have a prism, and on the top side of the prism we have a extremely thin layer of gold, and on top of this layer of gold potentially we have a stream of either gases or liquids, and these gases or liquids potentially contain viruses. With a very high probability, these viruses will get stuck there onto this layer of gold. And if this happens, then something very strange is the result. As a result, you will have a change in the reflectivity of visible light on the other side of this extremely thin layer of gold. And this can be observed by using a source of light and by using a camera. Obviously, being able to observe viruses in this way would be very nice to have in the case of the COVID-19 sensor, in the case of the COVID-19 virus. Our researchers are working on improving the detection quality for COVID-19, but it's not easy because safe training is not easy in the case of this sensor. Because of the small dimension, everything comes with a lot of noise. Next, I'm going to show you a little movie where you're going to see the noise. You're going to see patterns that correspond to viruses, or more precisely in this case, virus-like particles, to have safe experimentations. And later on, candidates to be classified as viruses will be included in blue rectangles, and if they are finally classified as viruses, they will be enclosed in green rectangles. Now I'm starting the movie. You see the amount of noise. Some patterns are popping up, some are included in blue rectangles, and many of them then actually finally enclosed in green rectangles. That means they have been classified as viruses, or more precisely virus-like particles. You see, some patterns are rather similar, but for one reason or the other they are not classified as viruses, and you can see from this little animation that data analysis is not easy. There are various ways in which we can do the data analysis. One way that we have been looking at is using a pipeline which is similar to pipelines that are used in computer graphics. Such a pipeline starts with pre-processing, where we have two hardware parameters, including, for example, sizes of the memories and the speeds of processes. We do have another step called signal restoration. Again, we have some parameters there. We have a third pipeline stage with additional parameters. We have a segmentation stage, and we have a classification stage. So this pipeline of analysis steps can be executed on a computing platform, in this case on an embedded platform called Odroid XU3. We choose that one because that one allows us to measure the consumed energy. Now, in order to optimize the detection quality, we have to find the best values for these parameters. And this can be done by running a genetic algorithm on top of this and by tuning these parameters. Doing this, we have been drilling holes between the walls between physics, graphics, machine learning, and embedded systems. And this allowed us to generate results that were not available within one of these disciplines. We are able to detect, to consider the trade-off between the detection quality and the energy consumption. In these 3D diagrams, you have in one dimension the detection quality, in another dimension the consumed energy, and in the third dimension the execution time. Now in this dimension, this is the corner where we would like to be. We would like to have the best detection quality. Also in this corner we would have the lowest amount of consumed energy and also the fastest operation. Now these blue boxes, they correspond to Pareto optimal design points, and you can see that we can either have the best detection quality but then we need more energy, or we can consume less energy but then we have to be happy with a lower detection quality. The gray points correspond to Pareto dominated points. This is the case of just optimizing the software parameters. If we also optimize hardware parameters, you can see that we can get much closer here to the sweet spot in the diagram. Now that was the first case where we were able to show the benefits of drilling holes. I'd like to show a second case where we are using machine learning to predict the data rate for mobile phones, and doing this in a passive way. The first phase is the training phase, in which there is actually some active component included there as well. During the training of an artificial neural network, we are looking at the traffic coming from the control channel. And in addition, we are providing some test traffic there to the base station, and we use this input to train an artificial neural network so that it is able to predict from just looking at the control channel what is the available data rate. So that means then during application we just look at the control channel, and using the artificial neural network we are able to achieve a good prediction error. If you look at this diagram at around here somewhere, we would have the value of 0.93 corresponding to 93%, where we have a data rate prediction of up to 1.5 megabits. If you also allow higher percentages, then you would have, if you would be going for higher percentages, then you would be around here, and you would have lower prediction errors. With some higher percentage rates, you would have slightly lower prediction errors. So in this case, we have been linking the communication world, that means communication using mobile communication. We have been linking that one to machine learning. The third example is that of data mining in astroparticle physics, where researchers are looking at the radiation which is coming from outer space. They are looking at the amount of neutrinos that are coming from outer space. They have been using machine learning for the data that has been collected at the South Pole using a particular sensor there. There were some deep holes that were drilled into the ice there, and using machine learning it was possible to figure out that there were more neutrinos arriving than that was previously considered. So in this case we have been drilling holes not only into the ice but also into the wall between physics and machine learning. The fourth example is slightly different in that we are looking there at model-based optimization. In this case we are trying to find the best treatment for cancer patients. And this is based on this diagram, which displays as a function of the genetic information of patients and a function of the medication, the survival times. In order to find the best medication, it is interesting to find one closed form function which models this experimental data as precisely as feasible. And in order to find such a function, you need to evaluate potential functions a large number of times. Fortunately, this large number of evaluations can be mapped to multi-cores, but the question is how many cores should actually be used. This depends very much on the execution times of these function evaluations. So therefore, we have been using machine learning in order to estimate the execution time of these function evaluations as a function, for example, of certain parameters. And from this diagram, you can see the color-coded runtime for the estimation corresponds pretty closely to the really observed runtime. Using this information, we can then guide scheduling strategies that result in a good utilization of the available processes. And the result can be seen on this slide, where you see that for a 4-processor system, we have a pretty good utilization if we use this estimated runtime. If we don't use it, if we don't use machine learning, you see that there are many idle times. So in this case, we have been drilling holes into the wall between machine learning and real-time systems. In a way, reversing the roles there, we have been using knowledge from real-time systems there in machine learning. In the final section of this talk, I'd like to briefly talk about education, because for education there is a question, do we need new degrees or not? We can teach CS or CPS education either by having a specialization for some existing degree, which would have the advantage of not having to introduce a new one, but there would not really be enough headroom to add the material which is needed, but the effort for the introduction would be lower. The question is, would this be feasible for cyber-physical systems? Therefore, it might be beneficial to introduce a new degree, even though it's not that well known. And then we would have a little more headroom for introducing additional material there. But there is a larger effort and we need more people, and still we have constraints. Some details can be found in a recently published special issue of IEEE Design and Test, for which there's a reference down here. Even with that approach, there is a question, how do we teach the students all the relevant knowledge? We can't really expect students to read dozens of books. So therefore, we have compiled what we consider to be essential in one book, so that the students can refer to that book. And the good news is that that book is available free of charge from the internet, and everybody can use it. With the availability of that book, there is a question, how do we really take maximum benefit of the time when students are available in our universities? And I'm therefore proposing to swap the roles of what people do at home and in the class. I'm proposing there that in the dorm or at home they should be reading relevant material like this book. Or if they don't like reading, they can still watch my videos, and in this way get an introduction to the topic. And then at the university, in the class, they could try to apply this knowledge there, working in teams and exercise teamwork. And I think that's much better use of the time in the class than trying to teach the material in the class. So this leads me to the conclusion of my presentation. Hopefully I've convinced you that in the future the applications of ICT will be linked to cyber-physical systems. Also, I hope that I've convinced you that there is an abundance of opportunities, which unfortunately also comes with a lot of challenges. One of them being the fact that many different disciplines are involved. I'm proposing to drill holes into the walls between the different disciplines. So, for example, we need to drill holes between different disciplines and data analysis. And I think I demonstrated that there are benefits resulting from the interaction of these different disciplines. So drilling holes into the walls provides incentives, and I think this is something that should be done. And finally, I had a few remarks on the challenges of CPS education, which are again linked to the fact that we have to talk about many different disciplines there, and it's really not easy to provide all of this knowledge to students. So this concludes my presentation. Thank you very much for your attention. And I apologize for not being available for questions because I will be undergoing eye surgery right during the conference. So thank you very much.